Hi everyone, welcome back to part 2 of lecture 16, and now we're going to talk about duality theory of STPs and an application in control theory. Okay, so before we do talk about duality theory, I need to define what is an inner product between two symmetric matrices. Okay, so if A and B are two symmetric matrices, let's define their Frobenius inner product as the following form. We have these brackets like AB, A inner product B is equal to the trace of A times B, which if you write it down is the same thing as writing like sum for every ij of entry ij dot times the entry bij. Okay, and this, if you think of the matrices as like long n square vector, this is exactly as the usual inner product as a vector. Okay, if you think of the matrix as a vector, this is like their Euclidean inner product. So then we have this norm that we call the Frobenius norm. Let me just put this as a F here instead of 2. Okay, so we have this Frobenius norm, which is just the square root of the inner product with itself. Okay, which is the L2 norm of them if you think of them as a linear space. Okay, and if we take this norm, we can talk about the polar dual to a given spectrohedron. And this polar dual is very special for some reasons that unfortunately we won't see today. Okay, so okay, now just like in linear programming, we can represent the STPs in standard form. Okay, and what is the standard form? And this standard form is going to look very much like the standard form for linear programming. We're going to minimize now our variables. Okay, they're going to be encoded in a symmetric matrix. So X is a symmetric matrix. These are variable constraints. And now what we're going to do is we're going to minimize C inner product of X. Okay, C is a matrix of constants, right? Subject to the inner product of AIX equal to BI. Okay, so these are going to be another constraints. So now the variables are encoded in this positive semi-definite matrix X. That's the condition that we impose in our variables. And remember, in the primal form for LP, we wanted all of our variables to be non-negative, right? So each constraint is given by an inner product. And note that the similarity with LP, right? So the LP was what? We had here, we had AX equals to B, right? So which is like every row, like AI transpose X is equal to BI, and we had X greater or equal to 0, right? And here we have C transpose X, which is the same thing as the inner product of C and X, right? Like in the Euclidean space, like Rn. So we're doing exactly the same. We're putting them in the same standard form. And now you may ask, okay, but how is this an LMI? Because how is this a linear matrix inequality? We have one linear matrix inequality, but why are these a linear matrix inequality? And the answer is, as usual, right? Like this is forming like a polyhedral set, right? If I don't talk about X being positive semi-definite, and I can just encode all of these inequalities in the diagonal. So this is the same. So this does give us a linear matrix inequality. Okay. So since we already saw it, I'm just going to go quickly over it. And now here's an example of the primal program, right? So if we have this minimize 2 times x11 plus x12, and now our input matrix here is positive semi-definite, and here is only one of the constraints. And if you notice, this constraint is given by these by this matrix and by this scalar, right? B1 is equal to 1 and A is equal to 1, 0, 0, 1. And the minimize here is like C times X, where C is exactly like this matrix here, okay? So, and notice which convex set is this semi-definite program is exactly the constraints are satisfied if and only if we have that this determinant of this matrix here is greater or equal to 0, right? Which is x11 times x22 greater or equal to x12 squared. And we also have x11 and x22 greater or equal to 0, right? Like x22 greater or equal to 0. But if we unravel this equation, what we get is we get the equation of the following circle, okay? So this is the equation of the following circle. And my coordinates here are x11, x12. And you can see that this semi-definite programming gives us exactly this region here in green. And if you solve this semi-definite program, okay, you can solve it in a computer program. You will get that the value of the semi-definite program is actually given by 1 minus square root 2. And the optimum is given by this semi-ugly formula here, this matrix. And note that both of them are not rational. Okay, this is very important because in a linear program, if the linear program was defined by rational entries, then you know that your optimum solution is rational, right? And you also know that it has nice bit complexity. But here, our solutions can be irrational and therefore um, can have infinite bit complexity, right? So we can only hope to get in optimization, we can only hope to get optimum solution, close to optimum solutions to semi-definite programs. Okay, it can be shown your solution is like an algebraic integer of a certain degree, but if you're doing optimization, you really want bit complexity, right? And therefore, to solve an SDP, you only want to find approximate solutions. Okay, so this is an example of another subtlety of semi-definite programs. And now let's talk about duality, since we already saw a lot of subtleties of semi-definite programming. So let's look at our SDP and let's do the same thing that we did for linear programming to try to find a lower bound on this optimum, right? We want to find a lower bound on this optimum. So, okay. So if we look at what happens when we multiply the ith equality constraint by a variable, by a free variable yi, what we get is we get that if we multiply yi times aix, we know that this is equal to yi times b, right? So this guy is equal to this guy. So if I sum, this sum on the left is equal to the sum on the right because they're equal term by term. And now if I just, since this is a linear inner product, right? It's just a Euclidean regular inner product. Then I can pull the sum here inside of the inner product. And therefore I have that the inner product of this matrix and X is equal to Y transpose B. Now, here's the thing. If we have that the sum, like this element here, is less than or equal to C in that positive semi-definite ordering, then we have that Y transpose B, which is equal to this big inner product, is less than or equal to C times X. Okay? And I just leave it as an exercise to prove that, if A less than or equal to B implies that AX is less than or equal to BX. Okay, I just leave that as an exercise to prove that. And now note that what we got is that Y transpose B will be a lower bound on the solution of our SDP, on the value of our SDP, right? So this is our value of primal, and this is a lower bound. So then we have set ourselves up for our duality, right? Because now we can just define the following program. So if I look at the primal SDP on the left, I can define the following dual SDP, which is to do what? I want to maximize my lower bound, as we saw, subject to, well, this is the condition that I need for my lower bound to hold, right? So then we can consider this semi-definite program as our dual. And from the previous slide, we saw that this condition, sum of yiai less than or equal to C, implies that Y transpose B is a lower bound on the value of the primal. And therefore, the optimum value of the dual LP lower bounds the optimal value of the minimal LP, right? And then we already have proved the weak duality between these two semi-definite programs. which is, if you have X a feasible solution of the primal and Y be a feasible solution of the dual, then we know that this inequality holds, right? So we prove our weak duality. And now we would like to say, well, do we have strong duality? And let's just do some remarks on duality to see what happens with strong duality. So, okay. And before we do that, we also have a theorem, which is not hard to prove, that if X is a feasible solution of the primal and Y is a feasible solution of the dual, right? If X, Y satisfy the following complementary slackness condition, which is a generalization of the linear program complementary slackness. And the condition is that this difference between C minus sum of YI times X is equal to 0, then we know that X and Y are primal and dual optimum solutions to the semi-definite program problem. And therefore, this is a sufficient condition on proving that the primal dual solution that you have is an optimum solution, right? So this gives you an easy way to test if your primal dual like pair is an optimum pair, right? So this is a sufficient condition to check that, oh, I have an optimal solution. I can check it, right? So I can also check that efficiently. And now let's talk about strong duality. And strong duality would be like a kind of converse to those two statements that we talked about before. And if I have a primal and a dual STP, right? So it turns out that strong duality for semi-definite programs is a bit more complex than in linear programs. Okay, and how so? Well, so it turns out that both primal and dual, they may be feasible. And remember, if primal and dual were feasible in linear programming, we knew that we had strong duality, right? That the value of the primal is equal to the value of the dual. We knew that. Now, for semi-definite programming, this is not enough. If both primal and dual are feasible, there are cases where strong duality does not hold, okay? And you will see this in your homework, okay? And now, but on the upside, under very mild conditions, strong duality holds, okay? So this kind of pathological case that we don't have strong duality is not really like a huge complication of semi-definite programming, okay? It's just a mild complication. And let's discuss some of these mild conditions. So one of these conditions is the following. So this is a sufficient condition, which is known as Slater conditions. And their conditions are, if the primal semi-definite program is strictly feasible, what do I mean by strictly feasible? It has a feasible solution X, and X is positive definite, okay? So X is not, doesn't have a zero eigenvalue, right? So if you have a strictly feasible solution, we call it the primal strictly feasible. And the dual is strictly feasible if and only if there is a feasible solution Y such that sum of YI AI is strictly lesser than C in positive semi-definite order. Okay, so these are known as Slater conditions. And a theorem is that if you have the Slater conditions, which means that if the primal and dual are both strictly feasible, then the maximum of the dual is equal to the minimum of the primal. Okay. So this is a mild condition, right? Because usually in practice, like the problems that we see, they are strictly feasible. So therefore, usually the programs have the same value. And the more general theorem of when does strong duality hold is just a little bit more general than this, but it requires some convex analysis for us to do, and therefore we won't do it here. Okay. So, but if you want to, like, you can read in the book that I referenced, in the end, you can read there and you can satisfy yourself and see when strong duality holds. Okay, now let's go to the last part of the class and let's talk about control theory. So now our setup here is Suppose that we have a linear system that it's given by this linear difference equation, okay? And this linear difference equation is just a discretization of a differential equation, okay? So I would have a differential equation if I have like dt dx like equals to, you know, axt, and then I can get like my dynamical system given by the differential equation. But here we're going to discretize it. We have the x at time t plus 1 is equal to a times xt, where a is a matrix and xt are vectors. And I start with the initial vector. Okay, this is called a discrete time dynamical system. And remember, this may look familiar to you because when a is non-negative and x0 is non-negative, then we have Markov chains, right? So, okay, there's a generalization of that to any matrix. And this is used to model time evolution, for instance, of temperatures of objects, size of populations, voltage of electrical circuits, and concentration of chemical mixtures. Okay, and it's used everywhere. And it's a generalization of Markov chains that you already saw. They're very useful. So a lot of people care about this. And the fundamental question again is, well, when this should be T. So when t goes to infinity, when time goes to infinity, under what conditions will xt remain bounded, let's say, or when will it go to 0, right? And when it goes to 0, we say that the system is stable, okay? That no matter where you start, like when you go to infinity, you're going to 0, okay? It doesn't matter. You will converge at a certain point, right? Which is the same thing as our Markov chain, like stabilizing. It's just going to a particular value. And if you shift that value could be 0, right? That point is no special very much. So, okay, and what are the conditions? So as we know from Markov chain, we know that the system is stable if and only if the absolute value of the eigenvalues of this matrix A, they are less than 1, okay? And note that this matrix A does not need to be symmetric, just like in Markov chain, okay? So the system is stable if and only if the absolute value of the eigenvalues are less than 1. Okay, these eigenvalues can even be complex, right? So, okay, now, okay, so we know this characterization, but let's look at it from the semi-definite programming viewpoint. Okay, so usually when you're studying these systems, these physical systems, usually people define this notion of energy, right? And Lyapunov functions are exactly a generalization of this energy that you have in your system. Okay, and what are they? They are just functions on xt that decrease monotonically on trajectories of the system. What does it mean? They are functions that if I start at a point x0, I want this Lyapunov function to be decreasing as I keep going, like t0, t1, t2, all the way up to infinity. Okay. So for our discrete time system, it turns out that we have a very easy Lyapunov function, which is the following. The function vxt, we can just say is equal to xt transpose times p times xt, okay? Where p is some positive semi-definite matrix, okay? And we will have this energy because we usually want energy to be non-negative, right? So we put P to be positive definite because we want this condition to be non-negative and to be positive whenever X is not 0, right? And okay, so we have this function for some symmetric positive definite matrix P. And now to make these monotonically decreasing, what do we need, right? So we need V of xt plus 1 less than or equal than V of xt, okay? And if we just unravel this definition here, I'm just substituting like this is V of xt plus 1, and this is minus V of t, V of xt, right? This has to be less than or equal to 0. I'm just rephrasing this inequality. But note that this is equivalent if now I replace every xt plus 1 by their definition in our linear system process, right? What is xt plus 1? Xt plus 1 is equal to a times xt, and therefore I also have like xt transpose times at transpose. But now, if I isolate xt, if I factor out xt, what I get is, well, this equation that I wrote a bunch on top. Let me just erase here. So this equation, like the second equation, the second inequality here is less than or equal to 0, and this has to be for any x, right? And this if and only if the following matrix, the matrix A transpose PA, right, which is this matrix here, minus P has to be less than or equal to 0, right? Like it has to be like negative semi-definite, right? So then we just saw that, okay, so a Lyapunov function is a function given by any of these matrices P, which is positive definite. And to make this monotonically decreasing, we must have this linear matrix inequality on that relates P and A, right? Therefore, it's very easy to show. This is a very easy theorem. You can solve it as a practice problem if you want. Is that if I give you a matrix A, an M by M matrix A, then the following conditions are equivalent. All the eigenvalues of A are inside the unit circle. That is, like all of them have magnitude less than 1. Or there exists a symmetric matrix P such that P is positive definite, and this matrix A transpose PA minus P is negative definite, okay? So this is a theorem that this stabilizes, the process stabilizes if and only if you can find such a Lyapunov function. But notice, these are linear matrix inequalities on P, right? Like A is a constant, so A doesn't matter. So, but these, the only variable we have is P. So then these are linear matrix inequalities on P. So we can use semi-definite programming to find P. Okay, so we can use semi-definite programming to find P. Okay. But you're like, well, okay, but this is a little bit contrived because I could also just check the eigenvalues of A, right? And why are we doing things differently? Well, you'll also notice that while describing this this discrete time system, we didn't talk about control at all. It's like, where is the control in control theory, right? So let's put control now in control theory. So in linear differential equation, like sometimes like we have matrices that appear right in our system. Sometimes our system gets matrices, like maybe we get matrices from the environment, or maybe we come up with matrices A, right? Like we may or may not have freedom on A, on the matrix A, but what we can do is we can interact with the system. So imagine that A is given to us and we don't have a choice. We have to work with this A. And sometimes A is not stable, right? Which means that A has eigenvalues that are outside of the unit circle. Then what we want to do, we want to introduce a control input, and the control input is this matrix B and these vectors UT, right? So this is our control input. Where B is some n by k matrix and U of t is a vector in Rk. Okay, it doesn't need to have the same dimension as the space xt. Okay, and what we're going to do is we're going to make at every point in time, like whenever the system is going to go from xt to xt plus 1, what we do is we interact with the system. We perturb the system a little bit. We have our input at time t, and then we use our control input and our natural input, and we make them interact to gain xt plus 1. Okay? So if we properly choose the control input ut, we can make sure that our system behaves in the way that we want. Okay? In our case here, let's say we want to stabilize otherwise unstable system. And if you think of this as like control processes, what we have is that at first what we're going to have is we're going to have our input U0 and then our input X0. And then we pass U0 through this black box B, right? This machine B, and B outputs BU0 to A. And then we input at the same time, at time 0, we input BU0 and X0 into A. And then A runs its process. A runs and gets us XT. And then it inputs back into itself, right? It has this feedback loop. And here we have to constantly keep putting, like at every time step, we control the system with our control parameter. And you can think of B as like a control machine. And then at every time t, we're giving both the control input and xt. And then we can perturb the system, right, to behave in a way that we want. But now we want to do it. If you notice in this slide, like this is very laborsome, right? A problem with it is that it's laborsome. And why is it laborsome? Is because at every time t, I also have to be inputting u of t. But we, as Waterloo people, we want to get rid of u of t, right? So what do? Well, we want to do it by setting the control input to be, some matrix k times the actual input that the process A is giving to us, right? So I have the process A. Process A at time t is going to spit out xt. So why not make our control input ut to be actually just xt, and then I convert xt into u of t by just multiplying by some matrix k that I just make it, I can just leave this in my device. So I leave it in my device pk. So now I just construct the device once, and the device will construct my control input, which now is bkxt, from the feedback that the system is giving me, right? So I'm modeling the feedback of the system to give a feedback to itself. And therefore, we transform this monster on the left side in green into this really nice process in blue. Okay, so this is equivalent to just saying that I have a matrix A plus B times K, and then I just let the process run from x0 and I just keep watching it, right? So this is the same thing as replacing the matrix A above as A plus B times K. And now this perturbed system, right, like this controlled system, is much harder to solve via simple eigenvalue description, because now I have to find B and K such that all the eigenvalues of A will be less than 1, right? But now, if you notice, this, like the way the Lyapunov functions way was a little bit more complex at first, but now it gives us the advantage that we can solve this system, this more general system, in the same way that we solve the easier system by Lyapunov functions, okay? So now, but in the same manner, we want P, which is positive definite, such that now, remember, we had A transpose PA minus P negative definite, and now all we want is this new matrix, like A plus BK transpose P, A plus BK minus P, bigger than 0, right? But now you may raise a bunch of red flags and you say, well, but what are my variables? Variables are P, which is positive definite, but we also have the matrices B and K, which are variables. So the system is not linear, not on LMI. So what's up with that? Like, how can we solve this by a semi-definite program if this is not linear matrix inequality? And the answer is that we can make it into an SDP, okay, with some matrix manipulations, which involve like taking some Schur complements and some inverses, and then renaming things, just like sometimes we manipulate linear programs to do what we want, right? So this can also be massaged into a semi-definite program with some matrix manipulations, which I won't talk about. Okay, so, and now to conclude, what did we learn today? We saw, again, the mathematical program is very general and pervasive in algorithmic life. And this problem is very hard, but there are special cases that are very striking. And we have been learning about linear programming today. And on Wednesday, we're going to see semi-definite programming. And semi-definite programming duality, again, are fundamental concepts. For semi-definite program is a little more sophisticated, but it gives us lots of applications. And there's applications in combinatorial optimization, as we'll see in the next lecture, on approximation algorithms for max cut, and applications in control theory that we saw today, and many more. And there is even like very much exciting work happening currently on connections between semi-definite programming and sum of squares, which is work that was done by Hilbert and a bunch of other people ever since the late 19th century, and it's being still carried out today. And there's this sum of squares connection to a semi-definite program, and this very bold attempt to have only one algorithm to solve all of the problems that we can hope to solve. Okay, so if you like Lord of the Rings, this is like one algorithm to rule them all. And this paradigm has been very successful in giving lots of efficient algorithms to many problems, matching many other algorithms that have been very creative. And this is not creative. This is just this one algorithm paradigm is also giving very good solutions to all of them, like with theoretical guarantees. So it's an amazing final project, and I just leave the advertisement there. Okay. And so the lecture today was based largely on the book by Blackerman, Perillo, and Thomas, which is, there's a link to it in the website if you want to get it. And also the Gaussian elimination was based on Ryan O'Donnell's lecture, and Anupam Gupta on SDPs. Okay. So there's a link to their course webpage also in our resources. Okay. And that's it for today. Thanks for coming. And I'm going to stop the recording.